Great. All right. So, hi, everybody. My name's Alexa Tartaglini. I'm an undergraduate working with Joaquin Vong and Brendan Lake at New York University's Human and Machine Learning Lab. And today I'll be presenting our work in which we show that deep neural networks, which have previously been shown to demonstrate a strong texture bias, actually demonstrate a shape bias when tested using a procedure that resembles the shape bias test used by developmental psychologists. And by the way, this is my first ever conference talk, so I'm very nervous and I apologize in advance if I make any kind of mistakes. All right, so let's call this object a DAX. Now, after viewing these additional objects, if I were to ask you which one of these is also a DAX, you would probably think that it's object A. And I know that because adults, when asked this question, would choose A nearly 100% of the time. And that's due to the fact that it shares its shape with the object I originally presented as a DAX. And this is something that we start to do in childhood. So around the age of 2, children begin to preferentially extend the labels of novel categories such as DAX to other solid objects with the same shape rather than the same texture or size or other dimension. This is a very well-documented phenomenon known as the shape bias, and it marks a very critical developmental shift in which children begin to realize that object shape is a reliable indicator of object names, and that facilitates early noun learning. So the standard developmental procedure for measuring shape bias involves a number of trials in which a participant is first presented with an anchor stimulus consisting of a novel shape and texture and some nonsense label like DAX or ZOT. This is followed by additional stimuli that match the anchor either in shape or texture, but not the other dimension. The participant is then asked which of these additional stimuli belong to the same category as the anchor. And the selection of the shape match at levels above chance across a number of trials indicates a shape bias. Now, as we grow older and we gain more visual and linguistic experience, this preference for shape information actually grows much stronger. Like I said earlier, adults, when tested with this procedure, will choose the shape match nearly 100% of the time. So this effect is very important in understanding how humans learn and generalize. Now, given the relatively recent success of deep neural networks, or DNNs, on visual tasks such as image classification, researchers have begun to question precisely how these models process images and whether or not they can be used as computational accounts of human vision. And in particular, this has led to a growing interest amongst machine learning researchers in measuring shape bias in DNNs. And while some initial work seemed to show that DNNs do indeed have a preference for shape, some newer work has painted a different picture. So in particular, in 2019, Garros et al. Devised a procedure for measuring shape versus texture bias in ImageNet pre-trained convolutional neural networks, or CNNs. They started by creating a set of test stimuli by taking the shape from one category and overlaying it with the texture of another category to get these Q conflict stimuli, which can be classified either by its shape or by its texture. On a given trial, a Q conflict stimulus is passed through a model to obtain probabilities for the 1,000 ImageNet categories, which are then mapped to 16 basic categories such as airplane, oven, and so on. Now, if the basic category that receives the highest score is the shape category of the Q conflict stimulus, the trial is considered a shape decision. On the other hand, if the basic category that receives the highest score is the texture category, it's a texture decision. And finally, if neither the shape nor texture category receive the highest score, it's a neither decision and the trial is discarded. And they finally calculate shape bias for a given model as the number of shape decisions over the number of shape or texture decisions. So they found that, unlike adult humans who are very strongly shape biased, ImageNet pre-trained CNNs are texture biased. And that finding was surprising and significant. It's generated a ton of follow-up work in which researchers are using this procedure to measure shape bias in a wide array of machine learning models. However, there's a number of important differences between the procedure used by Garros et al. To measure shape bias in DNNs and the procedure used by developmental psychologists to measure shape bias in humans, and which makes it kind of difficult to compare these new machine learning findings to the traditional findings. So first of all, as I was looking through these Q conflict stimuli that Garros et al. Used, I noticed that the texture is just very kind of overwhelming. You know, it tiles across the entire image and sometimes distorts the underlying shape, which might inadvertently emphasize the texture information while de-emphasizing the shape information. On the other hand, in the developmental setting, the texture of the stimulus is almost always contained within the shape of the stimulus, which reflects how textures map onto objects in the real world. Second of all, the use of model classification output for ImageNet categories limits this procedure to measuring shape bias for familiar categories that would have been seen during training, whereas in the developmental setting, they typically use novel stimuli in order to test generalization. And finally, the use of classification output like this just differs from the standard triplet-based procedure in which a participant is comparing an anchor stimulus to a limited set of match stimuli. And in fact, the procedure from Garros et al. Requires discarding a huge number of trials in which the classification output is neither the correct shape or texture category. So, motivated by these differences between the shape bias test from machine learning and the one from developmental psychology, we outline an alternative approach for measuring shape versus texture bias in artificial neural networks that more closely resembles the developmental procedure. We test a wide range of neural network architectures and training styles, and we find that generally the models tested exhibit a shape bias rather than a texture bias. So now I'll explain the developmentally inspired procedure that we use in our experiments, which follows the procedure from Landau et al. So a trial consists of a triplet of image stimuli, an anchor stimulus with a given shape and texture, a shape match stimulus, which matches the anchor stimulus only in shape, and a texture match stimulus, which matches the anchor stimulus only in texture. All of the three images in the triplet are then passed through a model separately up until the penultimate layer to obtain 3 vector embeddings of visual features. And then we compute the cosine similarity between the anchor embedding and the shape match embedding, as well as the anchor embedding and the texture match embedding. And if the shape match cosine similarity is higher, we consider that trial a shape decision, and otherwise it's a texture decision. So note that we don't have to discard any trials with this method. We generated a huge number of unique triplets like this for each data set that we considered, somewhere between 30,000 and 60,000. And after obtaining model decisions for all of these triplets, we compute shape bias as the number of shape decisions divided by the total number of trials. As I said, we test a range of both CNN and vision transformer models, including supervised, self-supervised, and randomly initialized variants, and all the details of these can be found in the paper. And now for the experiments. So in experiment 1, we examined the possibility that the really strong texture bias that Garros et al. Observed could in part be due to an overemphasis of texture information in the test stimuli. So in order to create a set of stimuli that more closely resemble the real world objects that are typically used in developmental studies, we altered Garros et al.'s stimuli by parametrically reducing the opacity of the background texture. And we did this by overlaying the original stimuli with a white mask of the background, the opacity of which is controlled by this parameter alpha. So when alpha equals 0, you just have the original Garros et al. Stimuli. And when alpha equals 1, the background texture is completely removed. So we created 6 distinct data sets using these values of alpha that you see here. For each data set, we generated all possible triplets, and we ran the shape bias testing procedure that I described earlier. And our results. So on this plot, the x-axis represents the alpha value, and you can see kind of an exemplar stimulus of that value. On the y-axis, we have the proportion of shape decisions, and the gray dotted line represents chance levels of shape bias. So anything above that line indicates a shape bias, anything below indicates a texture bias. And we see that when alpha equals 0, and we're just using the original Garros et al. Stimuli, this supervised ImageNet pre-trained ResNet 50 is very strongly texture biased, which aligns with what Garros et al. Found. However, as alpha increases and the background texture disappears, the model increases in shape bias. Just kind of ticking through the rest of the models, we found this pattern in every model that we tested. And when alpha equals 1, all of the models we tested exhibited a shape bias above chance levels. So this demonstrated that the degree of shape bias using Garros et al.'s Q conflict stimuli can be modulated by altering the stimuli to remove their background, which more closely resembles the developmental setting where the background is typically irrelevant. However, we realized that maybe in this alpha equals 1 condition, the reason why we see such a strong shape bias is that the anchor stimuli and the shape match stimuli have this perfect pixel level overlap. So we examined this. In experiment 2, we took the alpha equals 1 stimuli from experiment 1, and we varied their sizes as well as their positional alignments over a white background. And that also reflects the fact that real-world objects tend to vary in those factors. So we created 5 distinct size conditions as well as 2 alignment conditions. The aligned shape condition, where all of the stimuli are centered in the image, which creates this perfect overlap between the shape match and the anchor, and an unaligned shape condition where the objects are randomly placed on the image and there is no perfect overlap. So for each size and alignment condition, we generated all possible triplets and ran our shape bias test as before. And so in these plots, on the x-axis, we have the size of the stimuli, which you can see some exemplars of. Y-axis is again the proportion of shape decisions. And again, starting with this supervised ImageNet ResNet 50, we see that across all size and alignment conditions, it still demonstrates a shape bias, albeit lower for larger stimuli, which may just be because there's more texture present in those images. And again, we observe some version of similar behavior in all of the models, although there's some differences in how they respond to size. But the overall point here is that all of the models remain above chance levels of shape bias for all size and alignment conditions. And this strengthens our findings from experiment 1 by showing that the shape bias we observed is robust to stimulus size and positioning, and that it's not simply due to some pixel level overlap between the anchor and the shape match. So finally, in experiment 3, we take one more step towards matching the developmental paradigm, and we measure shape bias in all of our models using these novel stimuli with novel shapes and textures that are very different from the types of data that these models would have seen during training. And so on top, you can see an example of each shape that we used paired with each texture. And exactly in experiment 2, we varied the sizes and the alignments of these stimuli. So that is either the shape match and the anchor were perfectly aligned or they were randomly placed. And as before, for each size and alignment condition, we generate all possible triplets and run our shape bias procedure. So again, the x-axis represents stimulus size, y-axis is shape decisions. And just ticking through these models again, we see that they're somewhat less shape biased compared to experiment 2. And that also across both alignment conditions, most of the models decrease in shape bias as stimulus size increases, with the exception of this self-supervised Dino ResNet 50. And we leave the question as to why that might be to some future work. One really nice result here is that in the unaligned shape condition, the randomly initialized ResNet 50, which is this dashed pink line, hovers around chance levels of shape bias. And this is actually the average of 10 random ResNets. So that's quite nice because that's in some way what we would expect from a model with no prior visual experience. And notably, the supervised ResNet 50 and VIT V16, the solid pink and blue lines, demonstrate a higher degree of shape bias than their untrained counterparts for most of the size and alignment conditions, which indicates that that style of training may increase model sensitivity to shape information for these novel stimuli. So in summary, we show that deep neural networks with varying architectures and training styles demonstrate a robust shape bias when tested using a procedure that more closely resembles the developmental shape bias test, which is in contrast to previous results showing that these models are texture biased. In our first experiment, we showed that removing the textured background from Garros et al.'s Q conflict stimuli to attain a set of stimuli that more closely reflect the properties of real-world objects results in a significant increase in shape bias in all models tested. In our second experiment, we showed that this observed shape bias is robust to stimulus size and position. And finally, in our third experiment, we conducted our closest replication of the developmental procedure by testing the models with novel stimuli, which complicated the pattern of results, although we did observe that pre-trained models exhibited a higher shape bias relative to their untrained counterparts on these novel stimuli. So although it may seem like common knowledge that deep neural networks are texture biased, we found otherwise when we adapted the data set and aligned the testing procedure with how the shape bias is measured in studies from developmental psychology. And so just to finish up, I'd like to thank my collaborators, Joaquin Vong and Brendan Lake. I'd also like to thank Aaron Grant, Pat Little, and Pam Osborne-Popp for their valuable feedback on the paper, as well as the NIH for providing funding. And thank you guys for your attention and your patience with my technical problems.